Here are solutions to homework set number 6 for ECE 111, Introduction to ECE. This homework set looks at differentiation, a topic you cover in Math 165. Here, rather than finding the derivative by hand, we'll use Matlab to find derivatives using numerical methods. Now, the first problem isn't using Matlab, it's just sketched by hand. Given this function, plot the derivative versus time. So this is y. The derivative is dy dt. Here's t. So it's the change in y over change in t. So like between 0 and 1, y changes by 0 as t changes by 1. So the slope is 0 over 1. Between 1 and 2, y changes by plus 1 as t changes by plus 1. So the slope is 1 over 1, or 1. Between 2 and 3, y changes by 3 as x changes by 1. So the slope is 3 over 1, or 3. Between 3 and 4, change is 0 over 1. Here's minus 1 over 1, minus 1, 2, 3, 4, 5, minus 5 over 1. Then minus 2 over 1. 0 plus 1, 2, 3, 4, plus 4 over 1, and back down to 0. Kind of a sidelight. When you take Math 165, one way to find the maximum or minimum of a function, take the derivative, set it to 0. So right here, I know there's a maximum or a minimum. It's a maximum. Right here, there's a maximum or a minimum. That's a minimum. That's one of the uses of derivatives. So when you're done, the derivative should look like this. Derivative is just slope. Change in y or change in x, or t. Problem 2. Find the derivative of this function using numerical methods. Now, if you pad Math 165, you might be able to find this by hand. If you haven't, have no fear, there's Matlab. If I can get y into Matlab, I can find the derivative. So what I'm going to do is, given a function like this, that's sampled every so often, this is y, here's x. I'm going to take the change in y, right here, there's dy, over change in x, dx, there's the slope. So at points 2 through n minus 1, the slope is just the change in y over change in x. This is typical with numerical methods. The endpoints tend to have problems. I can't go to the left of the left endpoint, so I need a slightly different algorithm. I can't go to the right of the right endpoint, I need a slightly different algorithm. Here what I'm going to do is just take the derivative of the last 2 points. So if this is point 3, here's point 2. The derivative at point 1 is just do linear interpolation. That's roughly the derivative at 1. And likewise the right endpoint. There's other ways to do it as well. I could just take the previous 2 endpoints, say 2 and 1, and find the derivative. A couple ways of doing it. Here's one way to do it. Anytime you, well, once I get my function, I can then take y as a function of x, put that into Matlab, then compute. What is the derivative using numerical methods? Once I do that, I can plot x and y in blue, x versus the derivative in red. And here's what you get. Here is y in blue. This is the derivative, y prime in red. And a check. When y is a maximum, the derivative is 0. That checks out. When y is increasing, the derivative is positive. When y is decreasing, the derivative is negative. And you could actually check a couple points. Like right here, if I draw the tangent, it looks like y changes by 6 in about 2 seconds. The slope is about plus 3. And that's what you see in the derivative. It's actually plus 2.8. So there I found the derivative using numerical methods. Now again, note, if I can't find the derivative by hand, not a problem. As long as I can get the function into Matlab, Matlab will find the derivative. Try it for a different function. Here's another function, a bunch of sine waves. Get that function into Matlab. Y is cosine of x plus 0.1 cosine, I misspelled it, sine of 20x. Once you get x and y into Matlab, take the derivative, and here's what she looks like. So here's y in blue, and red, I've got y prime. Notice that differentiation amplifies high frequency terms. Okay, path planning. Suppose I want to go from 0 at t equals 0, and I want to go to 1 at t equals 4. How do I go from 0 to 1 in 4 seconds? Well, that's what we call path planning in robotics. A lot of ways to do that. Each different path, going from point A to point B, has an implication in terms of voltage and current. The voltage is roughly the derivative of position. The current is roughly the acceleration, second derivative. So I can do that in Matlab. Let's just input time going from -2 to +6, steps of 0.01, and I'm going to offset it by epsilon. The reason to do that is I don't want to have to worry about these greater than or equal signs. If I perturb it by a little bit, it's never equals. Then the angle is t/4 for t between 0 and 4, and it's 1 for t bigger than 4. And again, I don't have to worry about equals because of that perturbation, epsilon. So there's q. The derivative is just the derivative of t and q. The second derivative is the derivative of the derivative. Then plot it. So positions in blue, velocities in red, accelerations in green. And I'm going to clip y between -2 and +2. The reason being is when I have a step discontinuity in velocity, the derivative goes to infinity. Infinity doesn't plot very well, so I'm just going to clip it at +2, -2. So here's y prime, and y double prime. Now what this tells you is this is not very good profile. The acceleration goes to infinity. Infinity is hard to implement in hardware, so maybe this is not the best way to go from point A to point B. Here's A, there's B. Let's try a different approach. Suppose I have a cosine interpolation. I'm going to go like something like this. Between 0, for t less than 0, I'm at 0. For t bigger than 4, I'm at 1. And this is t equals 0. In between, I'll have a cosine function. So cosine kind of looks like this. This is minus cosine. I'll have a cosine starting from here and going to there. Equation for that would be 1/2 minus 1/2 cosine of pi t/4. The way that works at t equals 0, cosine of 0 is 1. 1/2 minus 1/2 is 0. Gives you this point. At this point, I want to be at pi radians. So in t equals 4, I have 4/4 pi. This is just pi. Cosine of pi is -1. 1/2 minus -1/2 is +1. So throwing that into Matlab, again, let's go from -2 to +6, steps of 0.01, plus epsilon. It's my perturbation epsilon. This is the function for t between 0 and 4. Here's the function for t bigger than 4. Once you get q into Matlab, find the derivative, second derivative, plot them. And here's what it looks like. So here's y prime, here's y double prime. So this looks like well, maybe a good way to go from point A to point B. The first derivative is finite, that's voltage. The second derivative is finite, that's current. So for robotics, that might be a reasonable way to do it. If this is an elevator and you have a person going up on board, people don't like jump discontinuities in acceleration. So maybe I'll use a different path. We'll look at that next week when we look at integration. calculate what I want, maybe what's better is to have the acceleration do something like this. That might be better. And you can do that. Just come up with different ways to go from point A to point B. Look at the first derivative, second derivative. Try to come up with one so the acceleration doesn't have these jump discontinuities. That's kind of what I would want. Problem 6 is finally another approach. If I do 0 for t less than 0, do a parabola going up for t between 0 and 2 seconds, a parabola looking like this between 2 and 4 seconds, and then a constant, I'll have a piecewise function. For t less than 0, a is 0. T bigger than 4, I'm at 1, that's point B. Between 0 and 2, that's t squared over 8. Between 2 and 4, working it out, this is a parabola that starts out at a half, winds up at 1, slope at 1 is 0. I guess that's all you need. That's this function. Throw that into Matlab, and again, kind of a long one. Here it is for t between 0 and 2. Here it is between 2 and 4. Here it is between 4 and infinity. Throw that into Matlab, take the derivative, second derivative, plot them, and now this is what it looks like. So this is y. Here's y prime and y double prime. When you take calculus, you learn that the derivative of a parabola is a line. The derivative of a line is a constant. So that kind of makes sense. This is parabola, line, constant. In terms of whether this is a reasonable path or not, maybe. If it's robotic arm, yeah, not bad. The current or acceleration is a jump discontinuity, another jump discontinuity, then 0. Robotic arms don't mind that. Current amplifiers don't mind that. If this is a person, people do not like jump discontinuities and acceleration. Again, what I would really like to do is have the acceleration do something maybe like this. If I do that, if this is y double prime, what is y prime and what is y? To do that, I would need to use integration, the antiderivative. That's what we'll cover next week when we look at numerical methods to integrate. That's also covered in Calc 2. For this homework assignment is just how to do derivatives using Matlab, stuff that you cover in Calc 1. Thing to note about this is actually fairly easy to do in Matlab. I just use numerical methods. Once I get the function into Matlab, I can find the derivative using this function. That's one way to do a derivative. There's other ways as well. Thing to note is, as long as I can get the function into Matlab, I can find the derivative using numerical methods. Now that's going to be kind of useful when you take Math 165. If you ever want to know, is my answer correct? We'll throw it in Matlab. Matlab will tell you that I don't know the equation for that function, but whatever the derivative is, that's what it looks like. When you take Calc 1, you'll be able to find out the equation for that function. It should match up with Matlab. And that is homework set number 6 for ECE 111, Intro to Matlab, using Matlab to find derivatives using numerical methods.